everyone. Thank you to the sponsors first. Thank you for organizing this event. It's a great event. So I'm here to talk about functional programming. And also, first of all, I prepared this in English. I understand that everyone here speaks Spanish as well. If you don't understand anything, let me know and I can translate. I speak Spanish as well. So this is a talk about functional programming, which is something that I really like. It's like my hobby. About me, my name is Zuzanna. I come from Poland. That's why the weird code after my name. This is my Twitter. And I've been working with Java for about 4 years now, recently in Kotlin, so everything in the JVM ecosystem. But I actually studied mathematics at university, and as I was trying to gain some software programming experience at university, I found some courses at the computer science department, and one of them was lambda calculus. I don't know if you've heard of it. This is the mathematical theoretical theory of the functional programming. So I took that course. I didn't understand anything of it. It's very theoretical, not practical at all. But then I started working with Java, and then I started learning Java 8 and specifically the streaming API. And I thought that this looks like something that I feel like I heard before. So that's how I got interested in functional programming. I tried to connect some things that I learned at university with the everyday job of software developer. So right now I work at SEAT Code. It's a startup set up by SEAT. We are based here in Barcelona. We are about 25 people right now, and we build solutions to innovate in the city urban mobility space. Okay. So, have you heard of object-oriented programming? Show of hands, maybe? Yeah. Have you heard of functional programming? Cool. So, these are two programming paradigms. Paradigm is a way of programming, and they are two different ways of implementing solutions in software, with software. So sometimes people think that they are totally opposite. That's why the love or hate sort of relationship. I think that they are just different ways of approaching problems. They are good for some problems, and the other one is better for some other problems. So what are they, more or less, very, very vaguely and in general? Object-oriented programming is based on objects. They say, well, the idea is that data is sort of an object, and the objects talk to each other, and they do things. And it's all around this idea of objects. And then functional programming puts emphasis on the functions itself, and it doesn't think that much about the data. So what functional programming wants to do is create a lot of functions that do single things, and then they can be reused and composed in different ways. And then the data is like the secondary thing. It's just the input to the function. And what that means is that in the end, in functional programming, the data is modeled a lot with lists and standards data structures, and not as much as like complicated objects that sometimes you can get in the object-oriented programming way. So how is this related to programming languages, you can ask? Well, so since these are different ways to approach problems, programming languages can be designed to make it easier to use one of these. For example, Ruby and C++ are languages that have been designed for object-oriented programming. They give you a lot of tools to follow the object-oriented principles and to do it well and to do it with a lot of performance. On the other hand, there's this language Haskell, which has been developed with functional programming in mind, and it gives you all of the tools to program in the functional way, and not so many to do it in the object-oriented way. So those are the sort of opposite spectrums. And then in the middle, we have a lot of languages that actually give you both of those things, and you can choose how to do that. For example, Python You can program in Python fully object-oriented way, or also in a functional way if you'd like to. Kotlin is also similar, so it's interchangeable with Java, so you can do everything that you would in Java. But you could also use a lot of functional things in Kotlin or Scala. Okay, but in this presentation, what I want to sneak in to you is a bit of Haskell. Haskell is this language that I really like. Slightly obscure, but getting more popular recently, maybe. What's special about Haskell is that it's purely functional. What this means is that it allows us to program in a pure functional way, just the way that the mathematicians thought about this idea before. And it's actually almost like a pure implementation of the lambda calculus, the theoretical mathematical thing that I mentioned before. What's another thing about Haskell is it has static types, and its type system is very well designed. So this means that anything that you have in Haskell has to have a type, and the type cannot change during the program, and that's why the static thing. And also, this is true for a lot of languages, obviously. But in Haskell, the type system is quite strong in a way that it also allows you to talk about languages, talk about functions, sometimes without even seeing the implementation, which we will see in the next part. Maybe some negatives about Haskell. For some people, this might be an off-putting thing. It might read a bit like maths, and it's just different from the more popular languages, so it takes a bit more time to get used to. But this is true of anything new that you might want to learn. So let's talk about the fundamental part of functional programming. There are going to be functions, obviously. So there are going to be pure functions, and this is the special type of function that might be different from any average or any random function that you might encounter in other software development projects. A pure function is a function that tries to be a bit more like a mathematical function, like you would talk about them at school, like f of x is equal to x squared, rather than a function, say, system print line or console log that is a function in a software developer way. So the first condition to be a pure function is to have no side effects. So let's first think of a very simple example of a function. Say we have a chicken, and then another one. And what we want to do is to find out which of these chickens is larger. So we take a function called max, quite simple, and we expect this to give us the larger chicken. So this function has no side effects in the sense that it is absolutely enclosed in its own scope. We take two chickens, we get out one chicken. There is nothing else that influences this function. So let's see how it's implemented in Java first. It's quite a simple code. I wrote it with the ternary operator. So what it says is that this is a function that returns an integer. It takes two parameters, integers, and then it returns this conditional. So if A is larger than B, then we want to return the A. Otherwise, we return B. Let's see the same function written in Haskell. Okay, so now we have this, which we would read as the function max applied to A and B is equal to, if A is larger than B, then A, so it's equal to A in the case when A is larger than B, and else B. So you might even think that this reads a bit easier than the Java one with the ternary operator. And that's one of the good things about Haskell, that when it's written in a nice way, it might read almost as a sentence, almost like someone explaining you what the problem is and what the solution is. Let's think about what is the type of this function. Like in Java, we could see that it was returning integer and taking two integers. So let's see how we write this in Haskell. In Haskell, when we want to define a type, and also, by the way, Haskell has very good type inference system. You almost never have to actually define a type. And when we write this in programs, it's for you to know, and it's for like the developer's own advantage. But this reads as, max is a function of type. The 2 colons is read as of type, from integer to integer to integer. And this is a bit strange because why do we have 3 integers there? So to make it a bit short and easy, let's just say that the last type is the return type of the function, and the types before are the arguments of the function. The reason why this is written in this way is because of carrying, and if you're interested in the topic, I encourage you to Google that, and because this is what allows Haskell to be quite performant, and it's also a very fundamental thing about functional programming. So for now, let's remember that the type of the max function is we take 2 integers, and they return us the 3rd integer, or chickens in that case. So let's see the second condition to be, oh wait, why doesn't it have no side effects? So this doesn't affect anything outside of the scope of the function. We take 2 integers, we return an integer. We didn't touch anything else. We didn't write to a database, we didn't write to a console, we didn't read from a console log. And all of these are considered side effects because they affect the state of the global application. And they might affect the execution of the function along the time. So we always expect this function to return us the good result, whether we run it today or tomorrow or in a different operating system between 2 integers. One of them will always be larger than the other. What is the other condition to be called a pure function? They have to be deterministic. And deterministic means that a function's output is determined by its input. So here, an example from life is when you have a jigsaw puzzle and you put it together and you get a picture of Jupiter, for example. Well, then you break it apart, you wait a month, and you put it together again. You're still gonna get a Jupiter picture, or at least you hope so. If you don't, then there's something really wrong with the puzzle. So this means that putting together the puzzle is deterministic. You always get the picture. This sounds quite obvious, but think of a function that gives you the time after some number of hours from now, for example, in 8 hours. Well, the input here is those 8 hours, but the output of the function depends on when you run the function. So this is the deterministic part. Is not always the case at all. But it has to be in a pure function way. So we say that pure functions are deterministic and they don't have any side effects. That means that they don't depend on global state and they don't change the global state in any way. Now, a very fair question from you would be, why do we care? Why is that good at all? And now think about it. If you have a function that are deterministic and have no side effects, say we want to test that function, what do we need to do? Well, first of all, let's think about other things of testing. I wonder if you ever had to mock some services or very multiple services or put some fake data into database or create some fake objects in order to test your code. So if we want to test a pure function, like for example our max function, what do we need to do? We just need to give it two chickens and then check if the one that it gives us back is the one that we wanted. We don't have to mock anything, and we don't have to put any fake data in the state to, for example, to simulate the conditions of the running program. We just give it the data and we check that what we got was the same. And that would be exactly the same with the other example. What else is good about pure functions? We said testing. Testing is easy and it's quite also certain. If you test your function and it works, there's nothing else that can happen there. What else? How about reusing? we have functions that are absolutely self-contained. They take input and they give you output. We can reuse them in any place without knowing the context. So it's quite easy to reuse them because we can just take them at face value. We take a function, it does this thing, so we put it in a different place and we can feel very safe about it and certain about it. And the last thing is, well, not the last thing, but the next thing is parallelization. So if we have functions that don't depend on anything and they don't change anything, and we can run them in parallel, and this is absolutely safe for us. And at the very least, it's much easier to parallelize and improve the performance of your program. And lastly, they can be quite easy to reason about, because to reason about the function, you only need to know the function, and you don't need to know the whole context of the application, because we already assume that the function doesn't change anything about the application, and it also doesn't depend on the rest of the application. So these are the good things. Now the next absolutely fair question that you might ask is, so the functions don't change anything, and they don't expect anything, and they don't depend on anything, so we can't do anything. So how can we do anything that our normal software programs actually achieve? Okay, so the functional programming's idea to handle the state that is inevitable, and we need to have it in a way, because otherwise we couldn't ever communicate to the user what we just did in our program. The idea of functional programming is that we try to maximize the number or the part of the program that is written using completely pure functions. And then this part of the program would be, for example, the core logic, the transformation of the data, and all of these things that actually are very important in the program. And then we get all of the benefits of the pure functions there. We can test them, we can reason about them, we can run them in parallel in a safe way. And then we push all of the side effects to the outside. So what we try to do is that we'd say that the logic with pure functions that is inside is wrapped in as small as possible layer of side effects that make this logic useful to the outside world. And that's just more or less what it would look like. And now, what does it actually mean in practice? How do we do that? And let me explain how Haskell more or less does that. So on the function level, let's say that we have a function on the top that maybe it gets the user's input, and then it does something to the input, so it calls another function and calls another function. So in this example, the function on the top has side effects, so it expects some input. But once it has the input, it can run it through pure functions, and the blue functions below are all pure. In Haskell, whenever you have side effects, the type of the function changes, or rather, the types that have to do with side effects have to come up in the type of the function. Otherwise, the compiler wouldn't know what to do about it. And they are the special types, and they are a bit like a sticky stain, so to say. So in the top function, we would be able to tell immediately that it has side effects. Just looking on the type, you would see, oh, this is one of those sticky, bad types. Well, not bad, the side effectful types. But then all of the functions that it uses below would have all the pure types, and we could use them, and we could test them, and we could get all the benefits. But then what happens is that, imagine that you have a pure function that calls a pure function, and then uses a function that has side effects, so the function that's sort of sticky. Well, then what happens is that the stain goes up, and because a function uses another function with side effects, then this function will also need to have the side effect in its type. So the stain goes upwards, and you end up with all of the free functions not being pure or having side effects. And so this is how you can control it. So if you write your program, you try to have the side effects on the top or on the outer layer, and the inside you want to have as pure as possible. So let's try an example on Haskell, an example that actually does something, although not much. So what we want to do here is, for example, communicate to the user, ask them about their name. Then we want to listen to the answer and get the answer from the user. And then we want to print a greeting to the user. So how is it implemented in Haskell in a pure functional way? This is what it looks like. And it's not very complicated. It's only 3 lines. So here we have the main function, and it does 3 things. Does literally using the word do. So first of all, it uses this function put string line, hello, what's your name? This is the same as print or console log or any of those functions, just in Haskell. Then what it does is it gets line, which is the same as read line, or don't know what it's in JavaScript, and it binds it to the word name. So we get a line from the user, and from now on we decide to call it name in our program. And at the end, we put the string with a greeting, adding the personalized part. So how can that be pure if it has obvious at least 3 side effects? So what happens here is that the main is of type IO, which stands for input-output. And this type is one of those special types in Haskell that lets you know that this is a function that has to do with side effects. And the thing about those types is that for them to be useful, Haskell expects that those types know exactly how to behave when they have to do a couple of things, one after the other, and each of them can fail for some reasons. For example, in this case, well, we might not have a console to print on, so it would fail. Maybe we don't get a line, or we get a line of different characters than we expect. And then again. So here what happens is that Haskell knows that this function uses the type IO, and the type IO is implemented in a way that it knows how to do a sequence of operations. And for Haskell to know that it has to use this functionality, we use the word do. So here is the result of running this function. Here we run the function main. It prints, hello, what's your name? We say Zuzanna, and it says, well, hello, Zuzanna. Very easy, and it works perfectly. And it's purely functional because of this type IO. And because if there was anything that would go wrong, then everything would fail. Hopefully that makes some sense. It's a bit weird. I sometimes think about it in a way that the IO type is almost like taking in the whole world as an input. So what we here say is that it's still pure because our input is the whole world, and the output is the same world with the console line changed to hello, what's your name, in a way. So that's why it's still deterministic, because for this instance of the world, it returns as the same instance with the printed line. So let's move on to another fundament of functional programming, the map operations. The map operations are used in a lot of functional programming, and if you have used the streaming API in Java 8, you will probably know more or less how they go. So let's see what they are. First of all, they are usually about transforming collections or lists or anything like that. There are different types of it. One of the types of map operations are the ones that transform a collection to another collection. And the other one is that reduce a collection of things to a single value of things. So starting with the function map. Let's see the type of the function map in Haskell. So as we talked about before, The 2 colons means type of. And this is a function map that is included in the standard library of Haskell. Its arguments, like we said, are these 2 things. And the last type is the return type. And with the brackets here, we mean a list of things of type A. And here, A and B could be any types, anything that you'd like. And what it means is that the arguments of the map function is, first of all, this thing, which means it's a function that takes something of type A and returns something of type B. The other argument is a list of things of type A, and we expect a list of things of type B. What does it do? The map function returns a list that is created by applying the given function a to b to each element of the list. But now note, I didn't say that it applies the function to each of the elements, because that would sound like we are changing the original list. What we are doing here is we're taking the list, we're applying the function to each element and creating a new list with all of the new elements. And this has to do with immutability, that in Haskell comes by default. Everything is immutable, so once created, we cannot change it. This helps with a lot of things. For example, that way we know that we give the function input and then we get an output, but it's not the input changed. The input will always stay the same, and we can compare them, we can do things with them. So how can we use this map function? Quite easy. Let's write our own function. Let's call it double. So what it will do, it will double all of the numbers in our list. So it will take a list of integers as an argument, and we expect it to return a list of integers. Like we said, map is a function that as arguments needs a function and a list. So here, how do we define a function in Haskell? Well, we write the name, the double, then the parameter. In that way, we say x's, which is like plural of x to know that we're talking about a list. And then we apply map to a function here that this is just doubling the number. In Haskell, there's a lot of syntactic sugar, and here we can just write times 2, and it will know that it expects a number. It will just multiply it by 2, and then return the result. And then we also apply it to the list. So the double function will go through the list, and it will apply the times 2 function to each element, and then return us the result. So if we execute it, what do we get? We get this. So this is the Haskell's interactive command line compiler. And here it says Prelude, because Prelude is the name of the Haskell standard library, which is always loaded when you run it. So first we define our function exactly the same as we did in the slide. And then we run the function with a list of numbers from 1 to 4. And sure, what do we get? We get 2, 4, 6, 8. Also here, note that this list hasn't changed at all. And this is a totally new list. So if you want this list to be a variable, well, a named constant, then we can use it in a lot of places without worrying about it being changed by other functions. Let's see the next functions. This was map. Now let's talk about filter. Filter is almost like a special case of map, but it has its own function. So filter's type is very similar to maps, but instead of taking a generic function a to b, it takes a function that takes anything and then returns a boolean. This is called a predicate. So what this could be is, for example, is the number even, or is number larger than 5, is the name a girl's name or boy's name, or anything like that. So here again, these are the arguments of the function. It needs a function, this predicate thing, and then a list to apply it to, and it will return a new list that will only contain the elements that for which the predicate was true. So if we say filter even numbers, then we'll only get even numbers. So let's see how to write that. And we're going to compose our previous function double with the new one. So here what do? So we write a function called double even of a type a list of integer to a list of integer. And then we define it as double even applied to xs. And now let's read it backwards. It will be a bit easier. First of all, we do filter even xs. And what this means is that we apply the function filter to two arguments, even and xs. And even is a function that is already in the standard library, the prelude, and it has the type exactly that, a tuple, or specifically a number to a boolean, and it returns true when it's even and false when it's not. So we apply filter to the predicate even and the list xs. So this will give us a new list with only the even numbers. And then we apply the same thing that we did before, map double to the resulting list. So what do we expect to get? Or first, can we make this slightly shorter and maybe even more readable? Yes, we can change that to double, which we already defined. So now this actually reads quite nicely, because we say that double even xs doubles filtered even numbers from the xs. And this is, again, shaping almost like a sentence, which is quite cool. So if we execute that, and we do the same thing as before, we just put it in the command line, and then we apply it to this. And this is another syntactic sugar from Haskell, and this just means that let's create a list of numbers from 1 to 10, and it's much shorter than enumerating all of them. And what we get, well, we get what we thought. So from this, we would get the even numbers, the 2, 4, 6, and so on. And here we get all of them doubled in a totally new list. And the last function in the map operations will be of type this folding, collecting, reducing thing. And this just means, like I said before, that this should be the last step of operating on a list, because this is what takes a list and returns just a single element. And it's called fold or collect or reduce, depending on the language and depending on who you're speaking to. And all of these names actually make sense. So fold means that it's like you had a list and you keep folding it like a material, and then you end up with just one thing. Collect means that you have a list and you collect it to one thing, and reducing is reducing from a list to one thing. What this usually does is that we need a function that accumulates things in pairs. So when we have a list, we accumulate the first and the second, and then we take the result, and then we take the third, and so on. The example here that will make it much clearer is the function sum. And it's a function that is already built in the standard library, but it's an example of the fold operation of the list. What it does is it takes as an argument a list of things, and this just means that those things have to be some sort of numbers, integers, rationals, or reals, or whichever you wish. And then it returns a single element of the same type, and it's called sum. So here we're looking at just the type definition of the function, but we probably know what it does. We don't need to see the implementation to understand what it does. And not only because it's called sum, but because it's called sum, well, we know that it will take all of the numbers, add them together, and give us back the result. Even if it wasn't called sum, having just this type definition would allow us to reason about what it might be. So since we know that A is a number, and to be a number, it needs to implement a couple of operations, for example, adding, subtracting, and the larger or smaller than, then out of these, the only thing that would make sense here is either adding or subtracting. And if you would subtract, then what do you subtract it from? Do you subtract the first from the second, or third from... It gets a bit messy, so you almost you can almost be sure that it will be summing the numbers just looking at the type definition. And we're not even going to see the implementation here. We're just going to use it on top of our example from before. So obviously, and the name is becoming a bit of a long, boring name, but it's called now sum double even. And as we would expect, we want to take our double even function from before that takes the even numbers and doubles them, and then we want to sum them all together. Following the way that we did it before, we copy the definition of the function from the previous slide, and then we put it in brackets, and then we take sum and we apply it to that. Why does it make sense? Well, as you can see here, sum takes just one argument, and then it returns the sum of the numbers. So we need to apply sum to a list. And we know that this function that we wrote before was giving us a list of doubled even numbers. But now the parentheses are becoming a bit annoying, I think. So let me show you how you would write it with the $sign. So now we write this, sum, $double, filter, even excess. Doesn't make any sense. But in Haskell, dollar is read as after. And it means that the functions are composed together. Like in mathematics, you can compose functions together. So here, if we read it this way, that sum double even XS, it sums after doubling, after filtering even numbers from the list of XS. Now, it reads like a sentence, and it almost makes sense. So let's see it in action. Again, we put it exactly like it is in the interactive REPL. We apply it to a list of numbers from 1 to 10, and sure enough, we get the result. Isn't this cool? Is anyone with me? Cool. So, what are the advantages of functional programming? What's in it for you at all, and why do we care? So once you get used to the style of the programs, they become a bit more concise and easier to reason about. This is with the idea that you already got used to it, because at first it's obviously going to be different and totally chaotic. So especially after time, it will allow you to understand what the function is doing. The same function of summing up all the even doubled integers in a list in Java probably would take 4 or 5 lines using a for loop, maybe in the streams 2 lines or 3. And here it was just 4 words. And once we read it the way that we could, it became quite clear what it does. So the programs can become a bit more concise, and if you're used to the notation and you have well-named functions, then it's easier to understand what it's doing. And especially if you write something and you come back to it in half a year, it might be a bit easier to understand what it was doing. Another thing about functional programming are the types. So we have seen that even just looking at the type definition of a function can help us, almost make us sure what the function is doing. So in a lot of the examples, a lot of cases, we don't need to go into the implementation of the function. If we know its type, we can already think about it, or we can use it, and we can just take it for granted in a way. Also, because of the type inference system and this very strong information that we can get from the type, just using the types and the compiler can help us be much more sure about our programs. Because if we implement a function that doesn't make much sense from the type perspective, then it probably doesn't make much sense. And it might just be that the compiler will not be happy about it and will tell you straight away that there's something wrong there, and it might help you develop better programs. And this thing, referential transparency, which is quite cool. I touched on very quickly on the immutability and the pure functions. So we remember pure functions have no side effects and are deterministic. So they take an input, give you an output. And then add to that the fact that everything is immutable, so once created cannot change. What that means is that if you apply a function to something and you get a result, a single output, and then you apply the same function to the same thing, it has to be the same output. There is no other way. And you also know that the input cannot change over time. So you can cache the result, and when you see the function applied to a thing, you can treat it as a value rather than a function application. So if you do it in the cases where it makes sense, obviously not every single time, then this improves the performance greatly. And this is what's called referential transparency. The last thing here is the parallelization thing. So because we can reason easily about our programs and we can reason about if they are pure functions or not, then we know that the part that's pure we can run in parallel, and we only need to be very cautious about it on the outer layer of the side effectful part. But obviously not everything is so great. There are also the pitfalls of functional programming. And here, actually I'm not going to focus on that a lot because this is about functional programming. But the one thing that usually puts people off might be that it's totally different. So it's not only different because the language is different to your language, but also because the approach to solving a problem might be completely different from what you're used to. So now think about when you learn a new language. If you are already in the object-oriented space and you want to learn a new language, say Kotlin after Java, this is not so hard. You need to learn syntax and some things about the language that makes it special. But in this case, you need to learn a new language and also a totally new, different approach. So it's going to be more difficult, but that's logical because those are two new things. And a lot of the times, it may seem like the concept is difficult because it takes time, but that's probably not the thing. The thing is that there is just, in practice, more things that are new to learn. And this may put people off because they think that it's difficult, but it's just that it's more thing. If you were to learn something totally new, like sewing or cooking that you haven't done before, then you would expect it to require patience. So this is my advice. Just have some patience if you're interested in that, and just remember that this is totally new and it's normal to take time to understand something new. And with this, we've arrived to the end. I hope that I made you a bit curious about the functional programming, and if you are interested in learning some of these things, I put on some links that have helped me in the past. For example, the Haskell.org is the official page of the Haskell platform. It's quite cool. I've seen that recently. When you open it, there's already a command line on the homepage, and you can play with it, and there's a tutorial to show you that it's not black magic. And the Haskell book is one of the newest books to learn Haskell. That's quite cool. It was written with the premise of one person learning it from another, and the book is written by the learner as she goes learning new concepts. So she makes sure that she doesn't write things that she didn't know before, so everything is explained. It's quite a nice book. And the exercism.io is a really cool page where you can learn a lot of languages, probably about 60 or 70 tracks. And what you do is you sign up and you solve some simple but quite nice exercises in your language, and then you get feedback from an actual mentor, and that helps you to take advantage of the language. And this was something that helped me greatly in learning Haskell, because I've been doing some algorithms, and then I would put it on the exercism page, and then I would get a reply from the mentor saying, no, you just translated Java into Haskell, that's not how it works. let me show you how to do it in a way that takes advantage of all the best things. So yes, thank you. If you have any questions, please let me know.